Video games here doesn't mean what we understand always by video games, but the similarity and the origin is the same. So first of all, I want to know if you do your homework, you have your laptops there, you have to download this program here, NetLogo. I will tell you how to use it. And NetLogo is a program intended to do research, in particular to start to do some research, some explorations of the system that you are interested to study. And after that, if you found something interesting, you can move to another more elaborate techniques to do this stuff. So, well, first of all, I will introduce you in how old are these video games for science? Because video games were first intended for doing science, to study complex systems, to try to find a computer that is able to think and to do repetitive works. So the first computer, digital computer, is for the 40s. And 10 years later, we have this development of tic-tac-toe, tennis, pool. There are a lot of this stuff that were developed first to know if we can do that, and then to study another strategies, to study how things work and try to model the reality, what we understand by real world, in a synthetic way. The idea is, if you can make a simulation of the real world here, we can run many experiments inside a computer that cost less and is less expensive in time and in resources. So the idea here is, this is the first video game that appeared for playing. It's tennis. This is a player. This is another player. This is the net. And here is the ball. And the ball follows here a well-known physics law, the reflection law. So most of this is indeed a simulation of a real tennis game with some simplifications, because tennis players are not bars, and balls are not square. But we try to put something essential taken from the physics world. Here is the reflection law. That means if the ball comes with this yellow line here and make this angle respect to the perpendicular here, he will bounces against the player following the same angle. So this is the first time. This is the main idea of how we try to represent the real world by physics laws in a computer, in a simulation. Note that now, if you are a player here, and this is a computer, you need that the computer take decisions. So we have two things important here. One, the computer have to do things by itself, by thinking by itself, which thinking is another loosely word. And we have to put some physical laws or some real world laws, because I will show you most of the systems I will show you are not from physics world, for physics, are for sociology, for geology, for economy. So the idea is how we can describe things of the real world using this kind of video games. Our first model is called the voting model, or the voter model. We have two candidates. We have this place here is a network. Each square is green or blue, and it reflects the opinion of the people if he will vote red or blue in the next elections. But people is influenced by their networks. So if I'm here and I have some opinion, I'm blue or green, and I have 5 neighbors here that are green and 3 neighbors that are blue, because green is the most has the large amount of population here, I will become green. But this happens for all the squares, all the dots in this network. So for the next one here, I have to see what's happened with all the neighbors inside, and then make if in average, which is the most populated color, and I will take the opinion of the most populated color. So because I have 8 neighbors, if there is a tie, if I have 4 blue and 4 green, I will remain in my actual position and I will not change. And these are the rules of the game. The game starts with a well-mixed population here. And then if you install your net logo and press Ctrl M and go to files and model library, and right here voting, choose this one. Here you have the opportunity to set up the model, and here you can see there are this amount of blue people and this amount of green people that think both ideas. So if we put the go button, you obtain this. So what we can observe is that people try to segregate and to get close to the people that share their own opinion. The question is, this is useful to gain an election, to win an election, seeing that these greens is the people that will vote one candidate and the blue is the people that will vote another candidate. Is there a way to make the greens win because they are more, or they can get, you can get a population all green? Can you try to do that? Each time you put setup, the systems start disordered, mixed, and if you put go, the system evolves to one situation. Here you can see that people not finished to put in a grid. This is a well-known result from physics because we are trying to understand how people vote and how people influence each other using a model that comes from physics. This is the way that physicists understand magnets. So now in physics, we believe that magnets are made of this kind of stuff, and after some time, if you allow them to evolve, you will get these domains. If you get all green or all blue, you will get a pole of one magnet. So these buttons here are switch. If I put this switch, this means that if I am surrounded by a tie, I have 4 blue neighbors and 2 green neighbors. Instead of being in my posture, I will change to the other side. So if I do that, or you do that, what happens? You will see that the people in the borders is all the time changing their posture, because the people in the border are the people that has half people in blue and half people voting green. So if I will change each time people influence me, the borders are all the time influencing. And there is a penalization here. There is another switch here that means if I saw that one candidate is losing by 1 point because I have 5 against 3, so I will vote the one that has less, because some people try to not allow that the other win. But if there is a very high disbalance, of course, I will vote the mostly because it's the most of the opinion. If you change this way, in this way, and you set up, try it by yourself. The evolution is slowly, but you can see that the green is larger or the blue is larger and the paths are larger. If instead to allow this changing, I change this rule, I can see that there is a border of people here. These people here are the people that has not decision. In an election, this is the people that the publicity try to capture, because the people in blue is always blue, the people in green is always green. So you can see how we have many different kind of configurations depending on the rules we put. And this is one of the disadvantages of a model, or one of the interesting parts of the model. When we are modeling, we have to decide what is important and what not. And here, and what is the rule I want to inspect and try to use to reproduce reality. So here you can see that in this kind of setups, with this type of rules, the populations becomes all mixed at the end. So depending on how you put the rules is your result. And modeling means this is the result I have expected. No, I want all in green. Can I obtain all in green? There is a possibility, but you have to discover that. Yeah. It's possible to obtain all in green. That is what I want, because I want all the people vote the green candidate. And it's possible to obtain this. Someone how obtained green or whole blue? No, it's my stuff gets frozen. Frozen. Yeah. Sometimes it's frozen because depending on the rules, if the rules are fixed, if I'm not changing because some rules, there is a problem there. If you have questions, if something is not working, just tell me. You have to install it. Yeah, I think so. One for them was a trade. It's fine? Okay. This program in particular is nice because it's easy. The programmation, it's really easy. This is the code in this here. Outside. Upside. You have this is you have the place for the simulation. You have place here that tells you what is this model, and it's useful to learn how to program in this. And you have a code here. And if you look that something is not useful for you, you can program in what you need. In particular here, we would like to get a graph that show us it's not working. I forgot something. But I can add a graph to see how the population changes, but maybe I make a mistake in the code. But let's go, because there are many models, and most of them are useful to understand things, and maybe you can use it in your works or just playing. This is a forest fire model. We start with a population of 3. This is a forest. Each green dot is a tree, and the other parts, the black dots, are parts without tree. So in the model, in the model, you can set up how dense this forest is. And then if you have few trees here, and the fire starts in this line, and you run go, the fire doesn't propagate because it cannot jump from one tree to other. But if we increase if we increase the density, we see that the fire can spread and sometimes reach the other border of the wood and eventually can burn everything. So there is a threshold here, a limit, a number here, that it's useful to see how much dense a wood, a forest must be in order to get completely burned. So here we have this phenomenon. We have these patches in a very dense forest, but if we decrease a little, maybe because there are some random situations inside the forest with a little less, the fire cannot propagate. So can you find which is the threshold in order to get the fire not propagating from here to here? There is a number that allows, look, if my forest is really dense, everything gets burned. The threshold is when I can put the fire here, from here, with the less dense forest possible. And this is called a percolation problem that is mostly used to study these things. This is a petroleum rock. The original problem of percolation is I have petroleum here inside this rock, and I want to take out the petroleum. In order to dry the rock and take out the petroleum, I need all the holes inside the rock must be connected. If I can connect one side with another side of the rock by the holes, I say that the rock is percolating, and percolation is useful because petroleum companies need to know if they are how much petroleum can be obtained from a rock. So percolations become one of the most studied problems in petroleum science. So this forest model is taken from this, and is very similar. Here, the trees can be modeled like holes in this rock. So someone have found percolation threshold? The minimum number, how much? 59? 59.
Yes, 59.
Okay, it's a good number. It's more or less 56, depending on, because you have, this is important. You have one realization of this. This is the experiment. Look what the importance of this. We are burning a forest. We cannot start to burn forests to measure how much we need, how much trees need to burn all the forest. But we can do the experiment in a computer many times as we want and study many times this and average over the solutions and obtain one value. So this is the importance of these kind of models. They are simple, but we can study a lot of things without burning anything really. So, well, I will follow, but something else I will show because it's slow and you can play with the models you want. This is called the Otelin's law, and is made to, until now we had set places. These squares are places, they are fixed, and we have rules to decide if these places change or not these colors. And the colors have some meaning for us. This is called a cellular automaton, and it was one of the first tools to model real world. In this model here, we have the patches, the bottom here, has some colors that reflects the influence of one of these dots. This dot is a seller. The seller tried to move close to the clients. The clients are these patches. And trying to obtain profit ganancias, revenues from its clients, trying to get closer to the clients. Also, these dots can increase or decrease the prices in order to get more revenue or get more clients. And they are competing in order to maximize their revenues. So this is, you do Control M and write hotlines. And then here you can set the number of stores. You start setup. Okay, it's not working in my computer, maybe in yours, but I don't know why. It will be easier if maybe there. Yes, it's something that is not working. Okay. Now, these are two sellers. They try to sell to people. People is represented by these places here. And the idea is to maximize the revenue. They can change the prices and they try to influence more areas here. Okay, I cannot show everything here. So you set up two sellers here, and you see at the very beginning, they share half of the clients. And when we say go, we see what's happened. For two peoples, the clients are all the time changing, buying to one or to the other seller. And sometimes there appear some spikes when the system gets divided. But the best profit for the two is obtained when they are together. If we... If we increase the number of sellers, we can see that the two of the upper part are competing. Okay. I do something.
Share the same number of clients. So the equilibrium contribution from the one that is decided, the same number of planets for the other one.
Yes, the two. I want to show when this, because accidentally I opened MATLAB. So there you have. So look, these two guys are fighting for the client. They have reached the equilibrium. You can see in the graph that the equilibrium is been reached. And this one that is a part of the other, it's all the time he gets the highest prices, and he gets less the clients and more the revenues. Because these two are all the time trying to take the clients of the other, and they are fighting for the clients. So this one has higher prices, works slower, works less, and have the more profit. And this is the Hotel's law. So one thing interesting here is that this part here, if I stop the simulation, this here is this boundary here can be mathematically described by an hyperbolic function. And you can see this is the part of this curve here that is, well, is something. But this part here describes these arcs. So now you can try to find which is the best strategy to obtain the higher prices, to work less, and to obtain the higher revenues. So this was a social example is taken from economy. The paper of this is from economy, it's not for physics. And indeed, I don't know any physical system that behaves that way. Maybe. Yes. Hmm? Yes. Mm-hmm. Okay. This is a most interesting, but is most difficult to explain, is how to obtain the Pareto's law. Everybody knows that there are few people that is of terrible rich, and there are lots of poor people in the world. This is described by this curve here. This means that this is an histogram of the distribution of the wealth. So there are few people that have a lot, and there is a lot of people that have few. And we can study that in this model when we can set people in the field. We get some kind of resource, and each square in the field have an amount of these results and a capacity. So there are squares that give more money or more resources than others. When each people is wandering there and looking for the place where the most resources can be collected. And then when they reach that position, they take the resources and consume part of them. The part that is not consumed is stored, and the amount of resources stored is the wealth. So this model can be obtained by, here is always write this word. This one is wealth distribution. There is another ones to play. And here you can see that there is a lot of parameters, because a model to reproduce reality most of the time needs a lot of parameters. The idea of the physicists is try to do minimal models. What are the 2 or 3 parameters? F equals n times a. E equals mc squared. We try to do that, to use the less parameters to describe the most of the world. But life, social systems are really complex. They need a lot of parameters. So with these tools, we can explore which of these parameters are really important and which are the ones we need. So here we have the number of people, the max vision of the people. If we put the setup, each one of these persons here have a vision that is randomly set between 1 and 5, because we put that as a condition. The metabolism is how much resources consume this person. It's only a random variable between 1 and 15. This is the life expectancy. I forgot to plug this. I don't know. Okay, so there is life expectancy, and this percent of this land is how much of this square has the maximum amount of resources, how fast the resources will grow again, and which is the number of grains that we can grow, the number of resources we can grow. So yellow here means a lot of resources, and black here means few resources. And then in the bottom, we have the class distribution. The red persons are the poor people, the blue persons are the rich people, and green are the middle class. If we put go, we see that quickly, the poor people is a lot, and the richest 6% of the population are few. And we can see how they evolve all the time inside. This Gini index, it's a measurement in economy to describe the inequality on the population and the wealth distribution. If Gini is 0, all the people have the same amount of money. And if Gini is 1, there means that one have all the resources and the other have nothing. So the challenge here, and the challenge for, I don't know, for politicians, is to try to put this curve at least even. At least even. So my best effort with this program is this one. It's almost linear, but it's the best I can do as a politician. That is why I do physics. So in this histogram here, we have the split. I split this result to see that indeed this falls like a power law. So can you be better than me distributing wealth? This is the question. Yeah.
Question comes at the end of the So can we go?
Yeah.
So this is a representation in 2D. Can I go to 3D with NetLogo?
Yes, NetLogo has many problems for doing really good science, because he needs a lot of memory, of virtual memory, and you always need to use this interface. So when you want to try to gather the results, it takes a lot of time, because it's all the time spending time doing these graphics and using the memory. So it's a really slow program for simulations. Okay? But it's very useful to start exploring, and I will go to that questions in 3 slides. So the idea is we measure a power law, and then we need to write some equations as physicists, because we like to do some mathematics on this, to describe that. And this most of the time is called population dynamics. Is common to use coupled differential equations that describe how much people are in which one of these categories. And we can relate these differential equations with parameters that says, if I lose money, where this money goes, or something like that. Yeah. In the same idea, this is only an agent-based model. There is nothing in the field here. There are no patches in color. And is how a virus distributed in a population. So we have the green population is the healthy people that can get an infection. These people is moving, and each time that moves and have contact with another person, there is a probability that to transfer some virus or infection to the other. Depending of the virus, of the kind of virus, this rate could be higher or lower. And also the people, the green people, get sick and get infectious because they have the sickness and the virus inside. The virus is with the person until the person gets cured or dies. And if the person is cured, becomes this gray here, this is a recovered person. And this is a model that very popular, really, well, everybody knows about this model because in COVID, this model was used for a lot of people, including people that never do mathematics before. And it's called a SIR model because you have a susceptible population, an infectious population, and a recovered population. So how much time you can be in this recovered population is how much I be immunized against the virus. So we have two important times here: the time I spent being infected and the time I spent being immune. You remember that coronavirus, you were infected for two or 4 weeks, more or less. And when you are recovered, you are immunized by only 3 months. But there are other diseases like, I don't remember now. But IR disease for the liver, that I don't remember the name now, that if you get the infection, you recover and are immunized forever. So these are an important parameter, at least in the first mode. So Control M, and here become virus. And set up. Most of the people is green, is healthy, and there are 10 people that has the infections, and you run the model, and then the population, you can see how the population oscillates. Depending on the parameters of the model, you can get all the people die, you can get all the people get cured, or you can obtain that the infection is always in the population all the time and becomes endemic. So all we know about sickness, we can put inside this model, study them. We can try to introduce a vaccine in this model so people get cured more faster or get immunized more time. And the idea is to model several kinds of virus. Well, I will go faster because there is not much time. There are questions because this will be easier, I think. That the idea is this is homework, it's not a talk. So Well, now we are close to what I studied with Fernando here. This is synchronization of fireflies. It's not true that fireflies synchronize. There are a few species that do this, but most of the species in the world don't synchronize. But the idea is fireflies see another firefly and with his light on, and then I try to synchronize my light with the others. And the idea is to get I put it up. Here it's useful to put this, show dark fireflies. So here you can see the number of the fireflies that are flashing at each time. The idea is to increase this number. If you see, because each firefly is looking to another and try to synchronize, the number of flying firefly is increasing, and it's increasing each time faster because there are because meanwhile there are lots of fireflies they can synchronize easy. This is described by the well-known Kuramoto model, and these models are also taken from physics. It was not intended for fireflies. So there are many rules here. You can try to understand. These are two kind of strategies to synchronize, taken from these fireflies. This regulates how long the cycle of how long the fireflies are blinking. You can play a lot with this stuff, and sometimes obtain useful or at least niceful graphs. This is one of the first models in which we observe collective behavior. So fireflies are all asynchronized, each one flashing when she likes. And at the end, we have all a behavior that all the fireflies are flashing at once. This is emergent behavior. We call emergent because we put a rule that says I'm interacting with my neighbor, but I cannot see what happens in the bottom. So the information that I take from this come from the other part of the room or not. If that happens, this is called emergent, because I can, if you put only the rules in the macroscopic level, you cannot address what will happen at the macroscopic level. No, it's quite clear. So, okay. Many of you. This video was done to hear the noise. These are thousands, more than 10,000 of starlings, a little bird, flying in Roma. All are moving together, are developing these figures, and there is nobody that says, hey guys, we are moving outside this over this roof. We will stay here. The information propagates along 10,000 of birds in less than a second. So it's not possible that if I hear and the 10,000 starling is in the other part of the room, I can say, hey, we go this direction. That is a kind of emergent phenomenon. If you put here in the logo flock, we can model this phenomena by setting a population of birds pointing in many directions. You can accelerate the time. And then we see that at the very beginning, they were moving in many directions, but because each bird is trying to align their velocity with the neighbors, this alignment that is very similar to the alignment of the magnets, but now these birds are moving, it leads to a flock that is moving in one direction. You can see again, start moving in many directions and form some clusters, and the cluster collide. At the end, you obtain this. Of course, here you can set up the range of vision of this bird and the separation between the birds, because they try to avoid to collide with the others, how much they can turn each time, because no bird fly to this automatically. Well, another thing. So if you put another configurations, if you put another parameters, you will get another configurations, or you will get that there is no possibility to obtain order. In this situation, order is never reached. Order is never reached because it's not obvious that order could emerge. What happened here? There is a problem here, sorry. Para esto. Okay. I don't know why. There is another slide, but it's not happening. I don't know why. Well, here is part of my work. But okay, it's here. Here, I will start to talk something about my work, because it's one of the aim of these talks. Here are some examples of things I was doing playing with video games. Here, we have this represents cancer cells in the brain. We have rounded cells that are not moving in the brain, and we have some cells that are elongated and try to move looking for resources. And if you start with a very disordered setup of this, we can see that under certain circumstances, the cells align and form these kind of these streams. This is like a flow of cells that are moving, and it's very important in cancer when cells move, because this is the way that the cancer develop invasions and develop metastasis. It's one of the origins of that. Invasion is one of the features, the main features of cancer, because in cancer, the cells grow without control, and if you have cells that can grow without control and can self-organize to do these streams, they become very dangerous. This is part of the work what we were doing with Fernando. We have some kind of particles that try to move. Each particle try to move where she see more of the other particles and try to get together the other particles, but cannot look all around. They can look only in a small cone of vision. So if the cone of vision is small, you can obtain this kind of worms where some leader. So the first particle is doing what he wants, and the other particles are following the particles in the front, and we're trying to describe this guy in stuff with Fernando. But if the particle can't see in many places, they form these structures here. We call them, they are like drops. And these drops sometimes collide, and at the end, we can prove that there will be only one big drop with a lot of particles like gas. And this is very similar to systems like when water and steam are in equilibrium in physics. So we can use a lot of things that we know about physics to describe mathematically these experiments in quotes, between quotes. This is another part, another situation of the same. We can see that the particles quickly form these lines. This is another thing. This is similar to the flows I show you for the starlings. And here we are studying how the particles that have the same color are all connected. So all these are flying together. All these greens are flying together. And here we study how these structures forms and split. And okay. Paso. Okay, well, you know all about that. And we are close to finish, don't despair it. So, well, the last one here is an answer to Fernando's question. This is a tumor growing in 3 dimensions. We have some kinds of cells I will explain soon. And in this movie, we can see this is done in NetLogo. There is a 3D version of NetLogo to do that. It's really slow because it requires a lot of memory. And the interaction, the way the NetLogo was built to be easy to be programmed is based in Logo. That is one of the first programming language. But that's the cost you have to pay to be easy is slow. It's too slow. Okay. Here. And this is one of the examples using NetLogo to do food science. After saying that is not good because it's my work, so I don't know if the science is really good, but it's what I understand about science. So here we have NetLogo simulations of tumors. These balls here are tumors that grow in a petri dish. So we try to understand how they grow, putting some rules. At the very beginning, we have always cancer stem cells. Not all the cells inside a cancer tumor are the same. And with the discovering of the stem cells in 2012, more or less, the markers, not the stem cell properly, but the markers, the stem cells research has become really important in cancer research. So we start with stem cells here, and then we let they grow. And sometimes a stem cell that is one of the pink here will get the her doctor, could be a stem cell, but most probably is a differentiated cell, a very specific cell. So the specific cells here are the blue and the cyan, and the stem cells here are the pink and the red. Red and blue means that they are able to reproduce, to get doctors, and the other ones cannot do that. They are quiescent. They seem that they cannot replicate, and they consume less oxygen and less nutrients. So we can prepare this experimental setup to get a lot of stem cells, or to get another, or to get a lot of these differentiated cells. And we run these simulations. And in these simulations, we try to address which is the threshold, the number, the amount we need to get stem cells in the border. This is important to understand metastasis, to understand how to deal with the stem cells and how to cure the stem cells. Radiotherapy and chemotherapy, usual techniques don't take into account this effect, because if the stem cells get caught here, when you put some venom here, some poison here, all these cells will die. But we know today that to get a tumor, we need a stem cell. So if we are killing all the cells in the periphery, always the stem cell will remain. And there will be very difficult to detect and to be killed. So that's why sometimes you run under chemotherapy or radiotherapy, you get cured, and 10 years after, you get cancer again, because it's difficult to kill something that is in the center. Of course, this is a simulation. We have a lot of rules that we are not putting here. We are only studying the geometry of the problem. And this is a percolation problem, and we can use what we know of percolation. This is the continuous line here, can be can be described by this line. These lines are not fittings, are from theory. And we can see that the theory of percolation is useful to address where the cancer stem cells are here. And well, this is one of my articles, is Science. So this is to show we have been playing all this hour with model that looks, I don't know, at least funny. But you can do proper science with this and publish papers and this stuff. So, and that's all. The only thing that I would like to give to you is this. This is the founder of the Boy Scouts movement, and he says that life is a game. So you can see in these presentations that from the very beginning of the computation of the computer games, science, we are trying to do science with computer games. So life is a game, and if we play this game, playing games, we can do good science or science. So thank you very much. Questions, clapping, everything is welcome. Or if you want to play,